higher on the more abstract.
Did you come to the that sounds
So working on getting the chat up. Hey, can I teach you the move? I'm gonna have a camera right here. And I want to be. You can sit behind me for sure. Sorry, I should like move our chair or else somebody else is gonna.
Very neuro, but lighter on the brain. Like on the using side more on the cognitive. So I have my own AI.
It's limited by its battery life. If you want something that's very low,
If you want low power, you wouldn't want something that's lower level than a conventional CNN type thing. Because if you're lower level, then you're going to burn more power.
well, it's supposed to be lower level, more power. It's asynchronous, so it doesn't have to be. And probably for as well.
But I'm still getting into how we integrate some of the more sparse approach to it now. It's more about how to do better
You have a macro.
Statements of language.
So that's actually exactly so yeah, it's a startup. I want to ask about it. I'm growing a little bit, but I've been
for like
because I've also been getting acclimated to
for anything with time series.
Okay.
You just feel like the overall, like a number of years ago, I read a book by Jack Hawkins. Reverse engineering the brain.
Let's see how we can go.
Oh yeah,
A lot of fintech.
a lot of fintech.
I mean, it seems like if you want
Eventually, I'm gonna go get some.
So I actually have to look at
You guys can just sit and watch.
you would want to
Something a little more general.
when I was abstract, I mean, something that does the job, but is not like firing individual neurons.
We can see if we
So,
can find a way to.
CNN, I would say, is more abstract than spiking neural nets. And so,
Sort of like a test.
Okay. What is that?
so you've got a very, I mean, in a TensorFlow type neural network. And we're saying inner product with a non-linear output. So that's about as simple as you can imagine. Whereas this seems much more complicated and low level. So, I mean, so that, I don't see how this is, it's certainly not going to win on power efficiency. The only thing it might win on is if the other one can't model something because it's, it's too abstract.
One of you guys.
David, thank you very much.
So yeah, so
From Maryland.
Yeah, I should. I was gonna try and tape this down, but maybe it's okay.
I took a whole tour of the National Library of Medicine and a bunch of different places, bunch of different institutes there, but that must be a real playground. That's so what are you up to?
I'm just visiting some friends in Berkeley. And just taking a vacation.
If you work in the neuro area or?
No,
more
I wish I
application.
could. I'm looking at.
Are you going to record the entire presentation?
I'm already live streaming it.
What's your name?
My name's Matt Taylor. I'm community manager for Nemental.
Live streaming meaning someone could log in right now?
Right now, yeah, it's live on YouTube right now.
Oh, wow.
Yeah, we would do this for all of our meetings, even our research meetings. I live stream every one I
Yeah,
can.
no, no, and you recording it in addition?
Yeah. Yep. If you go to search for Demenza on YouTube, it should be the live stream.
On YouTube.
Yep.
No human can really do. You can, we can look at things that are two-dimensional, and CNN is looking at the whole thing.
That's exactly what I'm doing. I'm using 3D CNNs for segmentation organs, and I'm also looking at the plaque. I'm trying to segment it.
So are you doing this as part of like the, some clinical thing that they're doing there, or are you just pure research?
It's all like pure research, proof of concept and stuff. Some of the stuff in the lab I work in has been licensed to corporations, but mostly just research.
Guys, can anybody hear anything?
That guy from UCSC.
Yes, Mark, I'm a guy. So I got all the wires down. I don't think it's
On YouTube, is the name Mementa, or is it Brains at Bay?
Dementa.
Process the
And there's actually 2 channels, so it's the one with more subscribers. We had an old channel we're trying to figure out what to do with.
Mobile network model.
You log into, so that's the network, and it's not secure, and then you log in.
We do it, we're actually not allowed to use the cloud for security reasons.
But I mean, even a local cloud?
We have our own GPU servers, which are
Okay, you can hear me. Okay, great. There's even people that will chat while I live stream. So I put up a little chat box beside it.
probably if we can use AWS, that would be very helpful.
How do I log
The more we, right now, we're
Are you mean in the Wi-Fi?
Yeah.
I don't know.
this summer we had some interns.
Settings?
They were using more GPUs, so we needed more GPUs. It would have been nice.
Oh, you're already connected.
It would have been nice if we could use like AWS.
You're already on the
Yeah.
Now, you open it, tries to connect. It works, you're connected. Oh, good. So now just search for YouTube.
Very secure.
Hopefully that's on your YouTube app
Cloud experience.
I wouldn't say that's a completely wrong perception. It's certainly less secure than behind one firewall
Maybe YouTube channel, just so you
I don't know.
otherwise you'll just go to our website.
And we have our own GPU servers. And actually, a lot of my work has started working there. It's just
People
installing
started
new
to
servers.
I hate to tell you this, but that's the camera that's live.
Server? Well, we have some custom boxes which have 4. Then we have the DGX station.
Play with that later.
Okay.
We're getting some new ones now from Micro, which are going to be.
And do you go for the real high-end ones, or do you go for the
Your live stream is
G4s?
up.
No, we get the ones for DGX stations have the Z100s, and these new boxes, they all have the low 100s, and we're getting 2 servers. That's like the top one.
Nice.
Yeah, because we need the big memory, like the 2 gigabytes of memory.
I mean, as far as I know, the one thing the V100s have that I think it's the Quadro 6000 doesn't is the double precision. So if you wanted to do like some quantum chemistry or something, then you need the V100s. But if you're just doing deep learning, I think the Quadro 6000 or maybe it's the There's a quadro that doesn't have double precision, it's strictly single precision, which is what you need. But it's either cheaper or I think it has more memory than
This is today.
That's like a beat yeah.
They're not dirt cheap. There's still quadros. If you want to go for a budget option, you go for the Titan X, I think, or the GeForce 2080 Ti or something.
Yeah, the Quattro is not, the whole Quattro series was really designed to get some more design, that good thing.
So there's, I guess, I think I misspoke. It wouldn't be the actual Quattro 6000, but there's what do they call it? They have a card that's without the graphics that is still that same chip. It's the same chip as in those high-end quadros, but it's a I think it's called the Tesla.
Tesla, yeah, Tesla accelerator, yeah.
So it's.
We have a couple of those laying around in our lab. We have a couple. Some of those are in some of our older workstations. Yeah, that's an accelerator. It doesn't have any video out.
Right. So NVIDIA just takes, it's the same exact chip. I mean, it's not like they've done anything different. It's just that, if you're working for, Lucasfilm or something, they can desperately need them to test it on Maya or something.
So they end up
we have some of those. They actually, I think we got a donation from the lab I worked at, got a donation from Tesla a while ago.
They did an AI?
You work in deep learning, you can apply, you can do academic research, but research, you can apply for free GPUs.
It's really compelling.
So do you have any
Yeah, I have
Right, and what I did was I did the dual booty, and haven't done it in and then it's going to sort of VM, but I've still got the dual booty there, and I want to undo. Yeah.
It's not that we didn't do that was the best thing to do, but hindsight.
It would be a lot easier to not do the
Yes. They use Apple instead.
So I guess it's the BIOS that you might have to do. Repartition your disk. And so what you basically be doing is you would give the space that you got for the new bunch of, you basically give that back to Windows.
In order to do that successfully, you have to know what you're doing. You used to say no more
See
than-
Falco's chatting. Hey guys.
In any event, thank you so much
So we got quite a few
for
people
alerting me
joining.
to this.
That's good.
I I dare, I ever heard of this meetup before?
I'm not sure.
before.
I don't even know what mic is existing. I think this mic's on.
Not only the top.
So I'm going to sit over here. I'm going to try and give you guys a view of Florian or the audience. I don't know, we'll switch back and forth. I got eyes on the presentation as well.
Yes, brilliant guy.
Glad you guys are watching. I can't tell. 15 people watching.
Really?
The YouTube thing kind of popped up, right?
That's what it's called. I think it's called the hierarchical.
There we go. 14, whatever.
The name, so it's not.
So Jordan, I think we're going to start at 7. Are we starting at 7?
Official schedule says?
Friday, we are starting at 7:10.
7:10. Okay. No worries.
Plus minus 5 minutes or 10.
Yeah. We've already got 14 people watching online.
Rock and roll.
Watching people eat pizza.
Wow. See, the online audience can beat the offline audience.
Not yet. Which is good. You want more people eating the room.
That's a challenge.
It's hard to know what I mean. Underscore.
Underscore, sorry.
Or a hyphen. I got it right the second.
Those who tweet.
Sorry about that.
But you might consider changing the writing style.
Florian always wears his lucky suspenders for presentations.
So they haven't had this. The next time they do it's meant to be a more abstract thing
Yeah, if anybody's watching, you guys please like the video. It's really helpful. Doesn't seem like it'd be that helpful, but it's super helpful. Everybody likes the video. I see there's 15 people watching. If everybody did the like button. Yes, I sound like that YouTuber. It's going to be an interesting presentation.
I've never heard seen it before, but it's such a
Yes, yes.
money, so we're not so you can go and enjoy it. Thank you very much.
That's also and then you show it the execution with a fake environment where you can navigate. So you're capable of
Anyone trying to put the HPN of GPU?
What's your name?
Matt Taylor.
Matt. Oh, you're the Matt.
Yeah, there's a lot of us out there, actually. Yeah.
Thank you.
Oh, you're welcome. Yeah, you put them on GPU, but they're not going to run super fast because one of the big benefits is the sparse operations in GPUs. I talked to this guy, I think one I hate to plug into this, but GPUs aren't designed to do sparse matrix operations. Our brain's networks are much different than the way GPUs are connected, so you're only going to suck so much out of it to make sort of better chip designs to take advantage of the fewer amount of computation required to do these types of networks.
Matt, what's your email address?
Matt@numenta.org. Or I can give you a card. I usually do that.
I have cards.
Thank you, Matt.
Or if I have
It's good. No, it's just months of recovery. You can't do them both at once, because then you can't really do anything.
Hello. Hi. What?
Hi.
We have it's on here. Okay. If you're gonna get started.
Do we meet at the HPN meeting?
Are we doing deep learning? The global nature of the way that so for the best investigating neuroscience biology and how especially loops that repeated the most essential part of intelligence.
That's the whole point of
It's a sensory motor loop. Right? There's a model in the middle of a simulation of reality.
I'm gonna
We made a lot of papers that for the users, and it's a good place to introduce, I think, to the way we think about space. I'm sure you'll be great. I'll be taking neurons and cortex for modeling space. And objects. No. So the nature of theoretical science is that theories are absolute. There's something, this is how we work based on evidence. So based on we always are looking at neuroscience research specifically. Okay, this presentation like Bayesian-Hebbian I started trying to understand how neurons relate to neurons. We're not trying to model understand exactly the circuits and what's being represented here. So we really screw out the whole part of years ago. Now, that being said, we have recently focused on deep learning because I think that some of the things that we've learned specifically by applying sparse semantics, which is crucial in brain theory. Sparse semantics, if we can make networks sparse, you get a lot less. You should be able to train them a lot less. Models, less power, less time. How can we submit theory and sparse representations in deep learning models? So we present some standard architecture systems. For example, take Hymnist with the Google speech commands we're working on like Resonant, and we'll typical model architectures of deep learning networks that we can build properly benchmark systems that are state of the art, and show how to use sparse without really changing the architecture. Just making sure that the connections between layers are sparse and they're enforced in a biologically reasonable way. It's important for the biology. Homeostasis is a big deal in biology. Making sure that sparse is applied properly.
They have an AI program and the neuroscience is here.
Oh, so you're still kind of at the precipice. Because if you hear, that's like everybody's involved. After the first year, they were like, that's how I realized I was really entertaining. So just so at this point, you go right at the pool about the
You guys are lucky it's working out. The internet's pretty good here. I think it'll be about 10 minutes or so before Floran gets started. And then I'll point this direction. But a pretty good turnout. Maybe 20 people here. About the same as we have online right now. You guys are representing quite well. Thank you for joining. Don't forget to like and subscribe to the channel.
So the question is that he's on the edge of
Right. See you guys. Right. No, you've been busy, it seems like.
Quiet happening.
Will we start in 5 minutes?
Yeah. I suggest everybody fuel up with lots of pizza, and then you have plenty to eat and to drink while I
We start in 5 minutes, so yeah, get all the bits.
Lots of beer before you talk.
Yeah. Right, yeah.
I think this is working a little bit better.
All right, we can try that.
Hey, looks.
Try that. I don't know where that should clip it.
That's better than that than now.
Right. Okay. Cool.
You can just mute it if you hit it once.
Yeah.
Go ahead.
That's all right.
All right.
Sure, it's all right.
Yeah.
You know if there's Wi-Fi now?
Wi-Fi's right there.
Oh, okay. That was easy.
There's a piece of paper somewhere that has it too.
Yeah, at Momenta we have like this very nice sign, you know, where as soon as we go live with a research meeting, that says like, you know, on air, just to make sure that we behave, you know, on screen. So now we have 1 to 2 cameras here. So just if you want to visit the stage and say hi to our online fans, do that too.
We're on the air.
You're on there?
Yeah.
All right. Okay. Sorry then.
Cool.
Oh, that's okay. No pressure.
Oh yeah. Oh,
We
yeah.
were on the air 20 minutes ago.
So, thanks. Welcome for the 3rd edition of Brain Day. So for the first time we're running at the university, so thanks UCSC for receiving us. There is no one from USC here, but maybe it's recording. So I'm co-organizing this event with Sam, who's here, Matt, who's there, Terry, who is not here, but she took care of all the foods and drinks, so she deserves our appreciation. We have 2 talks for today. That's Thomas over there and Floran. So thanks a lot for coming. So we are experimenting different formats, and we decided to do just 2 talks instead of 3 or 4, so we have more time for discussion. I think this will be better. And that's it. So we start with Floran. Let me see, I wrote an introduction for you.
Oh my god.
So the talk is about Bayesian-Hebbian learning, spike-based cortical network simulations. And Florian Fiebig, aka Flo, is a research science at Momenta. Here in his PhD at KTH, I can't pronounce that.
Kungliga Tekniska Högskolan.
All right, thanks. He's studying biophysically detailed supercomputer simulation models of the neocortex. He also conducted work on memory consolidation modeling, Hebbian learning, as you're about to see, and many other topics in both neuroscience and artificial intelligence. It's actually hard to find a topic Floran doesn't know about. It's an ongoing joke at Menta. Floran is also a talented musician, so I've heard of. He's a polyglot, and he's a major advocate of suspenders. So please welcome Floran.
All right, thank you, Lucas, for that kind introduction. Yes, indeed. So I'm sitting a little bit between neuroscience and computer science. My background is in engineering and computer science, but I fell madly in love with brains and retooled my life, did neuroscience on the side, and then, as a PhD, and that kind of gets you into it real deep. And so I'm gonna skirt the edge a little bit on both of these topics, which means I'm gonna write roughshod over both the neuroscience and the machine learning part, just in order to build a big arc that actually ropes in everybody into this conversation. So let's see how that goes. There's a couple of things I want to address today. So obviously we're going to talk about Hebbian learning and what it can do, in particular what it can do for Bayesian inference, and how might one implement something like that in spike-based neural networks, because of course communication in the brain is spiky. I'm going to talk a little bit about that, and how known cortical architecture can actually help with some of these problems, as opposed to complicating things with biological detail. Sometimes it's actually useful for something. So how do we simulate these things in a defensible way, and what might we learn from all of that? So just as a quick reminder, right, so this is overly broad, obviously, but if we're looking at machine learning, artificial neural networks, and neurobiology, we see that, the networks in machine learning have like these connected nodes, often with forward weights, whereas neurobiology is highly recurrent. ANNs are typically clocked or trained in batches, and whereas the brain is completely asynchronous, no neuron waits for another neuron to do its thing, right? It's biomolecular electromechanical machineries that run all the time. And so the activity is in spike and bursts and oscillations and whatnot, as opposed to big vectors that are being passed around, and you're learning continuously instead of like static data sets. And you have to learn on the basis of these spike traces as opposed to real valued gradients. Obviously that's an overgeneralization. There is a continual learning and reward learning and whatnot in machine learning too, right? So I'm not I'm simplifying things a little bit here. So then we're going to take a little bit of a look at Hebbian learning, what it can do for inference, why would one even want to use neurons for this, and then how, if one wanted to use neurons for this, spiking neurons, how would one do that in a biologically defensible way. I'm going to sort of skirt a little bit an attractor theory of neocortical function a little bit, because these recurrent Bayesian confidence propagating neural networks, BCPNN, it's a mouthful, but you'll see what I mean, are actually very good memory models. And I'm going to skip a little bit over the evidence for Hebbian learning in cortex. And then finally, I'm going to try to show a little bit what these kinds of systems can do in terms of both as an inference engine as well as an associative memory system. So let's get going. So, spiking neural networks, right? Neurons are not units. Neurons are, big, complicated biomolecular machines, and they don't communicate with real valued numbers that are being passed around or bits. They communicate with spikes. Spikes are like these very brief events, right? So just about a millisecond activation peak half width. So they're very fast events, and they're sort of discrete things. And then on top of that, when you look at neural activity, it's not just individual spikes. They often come in like these burst packets here, where like many spikes sort of bunch together in these gamma bursts, and then you might get multiple of those. So the method of communication is clearly very different from what we might see if we record from a bus. So if we dig down a little bit on that, just to refresh everybody's memory, right? So here you have a synapse, there's a synaptic cleft. You're going to have some spikes or spike train coming in, which is going to open some voltage-gated calcium channels. Those calcium channels are then going to release vesicles. These vesicles are filled with neurotransmitter, and with the help of two different proteins, they kind of bind to the membrane, and then the calcium can buckle those proteins in order to release the content of the neurotransmitter inside these vesicles into the synaptic cleft. And about half a millisecond later, like this neurotransmitter will bind at the postsynaptic site and open these channels for sodium ions to flow in. So now you have a massive influx of sodium ions, which is going to change the postsynaptic potential. So the membrane potential on the other side, right, on the receiving neuron, is going to change as a result of this pulse train up here. So if we take a look at what that actually looks like, so here you have a spike train, right? There's like a brief gamma burst here, so an 80 hertz packet of like 4 spikes. Then you wait a little bit, and 100 milliseconds later, you have another big short packet. And there is, as a result of that, of those spike trains, you now get a current into the neuron, and that current changes the membrane voltage. So this is the postsynaptic expression of these spike packets here, right? So this is the propagation of what we call a theta-nested gamma burst, because there's a theta oscillation here, so like a 10 hertz oscillation, and on top of that you have like these 80 hertz spike packets which are riding along. The deflection on that is a lot lower than the deflection you might need for initiating a spike. So a single synapse will typically not make a neuron fire, right? You see the difference between the resting potential at minus 70 volts and the firing threshold at maybe minus 55 in a typical pyramidal cell, like 80% of the neurons in neocortex. It's like some 50 millivolts, and the deflection that you get from like a fast spike packet here is, maybe 1, 2, like 2.5 millivolts maybe, right? So you're gonna need many synapses to cooperate, and you're gonna need spike trains as opposed to single spikes to really tick off a postsynaptic neuron to fire. All right, that being a quick recapitulation of biology, let's move on to sort of some of the machine learning part of this, Hebbian learning. Most of you will be familiar with Bayes' rule, just the simple idea that the probability of a conditional event can be sort of inverted if you know the priors of the events A and B, which turns out to be very useful if you're building a naive Bayesian classifier. So say you want to classify, right, some outcomes Y on some conditional, some attributes X. You get all the conditional probabilities of the inverted order here, and if you know your priors and your posteriors, you just get this very nice multiplicative expression, which you can then transform into the joint probability over the two priors, and you have all these big products in there. Now, what do neurons have to do with that? Well, artificial neural networks are really great summing devices. How does that help us if what we want to do here is really massive amounts of products? Well, there's a little trick. You just take the logarithm and you're doing this thing in logarithmic space, and suddenly all the products turn into sums. Now in logarithmic space, you can use artificial neurons to do this kind of a computation. So if you're working in logarithmic probability space, then you can use a neuron like that to do Bayesian inference. So there's a couple of problems with that, which I will already allude to here right now. The first one is that we typically have partial knowledge. So not all the variables that are necessary to classify properly are maybe known. And of course, the naive Bayesian classifier has a very strong independence assumption. So you're presuming that these different attributes X that you're using here, right, are actually independent of one another. Or at least independent enough such that you can apply Bayes' rule. And then the third problem is that oftentimes when we're building these classifiers, these are continuous variables. And so how are you going to do this now with sort of some probability on some attribute being true or false? So you kind of need to have a way to map those. We will return to those problems. Before we do, let's take a quick look again, swinging back a little bit to biology again. So this whole talk is going to be a bit of back and forth between the two. And we're going to talk a little bit about cortical columns. Obviously, we think a lot about cortical columns at Numenta because they're sort of an important piece of the research. So if we look at neurons in the brain, they tend to be very nicely vertically oriented very often, and they tend to cluster in these nice packets, which we call them columns, sort of like vertically integrated structures of data processing, where the cortical sheet really can be nicely discretized into these repeated units. And most of the data processing is going vertically and not horizontally in the sheet. And so you can build a neocortical sheet by producing many of these columns, repeating them, right? We call them macro columns or hypercolumns. And then if you take a look at what these neurons in that sheet actually respond to, so these are recordings from, I think, a tree shrew and, I don't know, some other mammal, maybe it's a rodent cortex or something. And so you are measuring here the orientation selectivity of neurons in that cortex. So you're taking an electrode down the cortex and you're measuring what these neurons respond to. And you find these very nice little patterns where you find inside these repeated structures. Do I get a click here? Is it dying on me? No, it's not dying on me, it's just slow. Hello, hello. Yeah, I don't know, this clicker is having trouble. Okay, let's use the cursors instead, that's all right. So you find these structures where all the different orientations are represented around sort of some node here in some sort of an interval code, right? So whereas you can go deep into the cortex and all the neurons are going to respond to a similar orientation, and inside the volume of one of these hypercolumns, you're going to find all the possible orientations represented. Now this turns out to be a very useful data structure. So you can sort of build an artificial model of that by saying, okay, I'm going to have a pool of inhibitory neurons and pools of selective neurons, and I organize them in such a way that different intervals of the spectrum of the attribute I want to code here are reflected on these different mini columns, so these subunits. And then they can all inhibit each other and compete for activation through a pool of inhibitory neurons, such that when one of those activates, it's going to shut down all the other ones, which gives you very nice information contrast, similar to what we observe in visual cortex. And so keep in mind, right, that when I say a mini column, that's obviously in reality a collection of cells, right? So in particular, the recurrently connected layer 2, 3, so the upper layers of neocortex. So why is this useful? Well, there's 3 different things we can take away from this. One is sort of this idea of nested columns, which we might want to test drive and what it can do. One is the interval code, which nicely, with these selective mini-columns, which nicely fixes the problem 3. So we can now map continuous variables onto these different mini-columns. And then these mini-columns can have probabilities of activation, and that way we can map now these continuous variables in that problem. We also get automatically a decorrelation of the different inputs through the inhibition, meaning there's going to be a winning mini-column. If one mini-column is strongly enough to say, I know what this is, then it's going to shut down all the other ones, which gives you nicely independent input parameters if you want to do now processing with these kinds of units. So now back again to machine learning. So you want to use these kinds of organized structures now. So nested hypercolumns and mini-columns. And so maybe you recognize the original problem here, right? So you have these different attributes and these weights, which are now obviously going to be logarithmic expressions of co-activation of the outcome variable y and the different attributes, normalized by priors and posteriors, and you're going to have some bias term for the postsynaptic activation. And so then you can simply map these data structures and treat them as inputs to compute the activations in one of the mini-columns. So now you have a Bayesian inference engine, and you already know how to build your biases and your weights in this logarithmic expression in order to make that system work. The one thing that you now need to do, of course, which is a bit of a complication, is that you're going to need to have an exponential for the output because you're working in logarithmic space, and you need to renormalize the output from all the different inputs, which nicely also solves the problem 1, namely that you can now have unobservable variables, and that is not really a problem. Because of course in the denominator here all the x's, right, that get summed or producted up without the logarithm, right, are the same for all classes. So the order of the different probabilities stays the same, and once you renormalize, you're going to have one winning pattern. So, but you now need to have a running estimate of the prior, the probability x, the posterior, the probability y, and the co-activation, the probability x and y active together. So how can you do that in a biologically defensive way? In a way that we can defend, right? In a way that is plausible. And so again, now I turn back to biology. So we somehow need to have a local spike-based rule because, you know, real neural networks work with spikes. So we can't just use, you know, simple, straightforward correlation rules. It's going to need to be a little bit more fancy than that. But it needs to be local information because there's no global state, of course. And we're going to see if we can use these modular recurrent structures to get something useful out of it. So this is not much what I'm going to talk about.
You use the word recurrence, but I haven't seen anything looping back.
Mm-hmm.
At some point, would you clarify?
I will clarify. Actually, the section after this one. That's a good point. So one of those is that the units inside the mini-column are highly recurrent themselves. So all the nodes that locally select for the same features also have a higher than chance probability of connecting with one another. But there's going to be recurrence beyond that, and that I will get to in the next slide. This work that I'm now talking about is work of a colleague of mine, Phil Tully, who did his PhD just a year or two before me in Stockholm, who found a way to nicely map such a Bayesian learning rule onto spiking neural networks. So you now have two spike trains of connected neuron pair, I and J, so the pre and the postsynaptic neuron, and you have these spike trains, and you're going to do now something that is super common, which you've already seen, that these neurons do, namely they have some kind of a temporal filter to aggregate the spiking, right, to build a postsynaptic or presynaptic trace of the activation. That's what you saw in the voltage traces, right? This is of course normalized now to some maximal firing rate, and also assumes to avoid underrun from the logarithms in minimum firing rate, but these can be very, very small epsilon. So you essentially get an exponentially weighted moving average filter of the pre and postsynaptic activity. Now why is that useful? Well, if you want to do Hebbian learning, then we're going to need to learn, for example, this co-activation here, where these units are actually together. and we don't want to grow a strong weight when they are not active together. So you can do that by doing this kind of computation now on the pre and the postsynaptic side. And you don't really need to understand all the different stages here. They have different biological justifications. But the main point is that you can determine a product of the pre and postsynaptic activation traces, which is going to give you a Hebbian component, right? So those are the cases where they're fired together. And this kind of a product will be useful for generating this exactly logarithmic co-activation weight, which indeed then shoots up as soon as these two neurons are firing together, and now they are wiring together. This P trace goes up, which builds up a higher weight. Similar for strongly active units, right, where we have then a strong prior or a strong posterior, as in this case, you get a corresponding Bayesian bias for your network. So now we have a way of taking a spike train, right, from a spiking neural network simulation and turning it into connective weights that we can use. So how do we now turn this into a recurrent neural network that leverages all these awesome things about attractors and whatnot? Well, you simply convert this theoretical structure into something a bit more biophysical. So you now argue that these mini-columns are actually subsampled units. And you can build a network from those. So you're simulating now a little piece of subsampled neocortex, where the pieces that are now co-active together, say they're coding for the same orientation angle, right, are now wiring together. You had a question?
Yes, in the previous slide, could you explain those parameters?
Sure. We can take a quick detour. Which ones?
I guess the taus, Fmax,
Right.
T-spike. I think
Sure.
the T-spike is the time of the spike.
Yeah, that's the time of the spike. The epsilon is the minimum assumed firing rate. Fmax is simply to normalize the Z-trace to some maximum assumed firing rate.
Okay.
The tau here is simply the synaptic time constant, so you can fit that. If you have an AMPA synapse, that would be 5 milliseconds. If it's a slower synapse, NMDA trace, 100 milliseconds.
How do you choose the tau E and tau P relatively to tau Z, and what is kappa?
I and P are simply all pre and postsynaptic pairs. And the kappa is a nice, it's simply a modulatory constant that allows you to temporarily boost or suppress plasticity. So you can use it for modeling dopaminergic plasticity modulation, for example. Essentially, it switches on or off the plasticity of the synapse. Right? If K goes to 0, then the update of the PIJ, right, the update of the weights, the updates of the pre and postsynaptic averages will stop. So you're going to freeze the network. So it's essentially a learning signal. And then the main learning time constant is the tau P.
And is there any physical meaning of a single spike in this case?
That is a really good question. I think we're going to have to return to that. Because I think
the reason why I'm asking this is I'm aware of the neurosampling literature.
Right.
So they do Bayesian influence by sampling, and every spike is basically a sample.
Yes. It gets very complicated because it depends on the type of coding, right? Because this type of a code obviously is very similar to a rate code because you're averaging over several spikes here and you're just convolving them with the kernel. We are doing that because we argue it's biological. It's what the postsynaptic membrane does intrinsically because of its time constants and what the receptors do because of their synaptic time constants. So these have some biological justification, but they are far abstractions in order to make it possible to build a network like this. So you now have a sheet of these mini columns, right? Keep in mind, every one of those nodes is again not actually one unit. There's actually several spiking units and they're connected, both locally, recurrently, there's connections particularly in layer 2-3, but they are also connected between the different mini columns, right? And these connections can now be learned. So actually what you're learning is spike-based connections here, right? But we now have a spike-based learning rule, so we can learn these connections. And that allows us to build cortical attractors. What do I mean by that? So you now have a spiking neural network, you have some cells, let's say, you had all those red mini columns marked, right? So all of these are active with some, random, irregular firing, and all of the ones that don't belong to that are active with some irregular firing. And if we now force stimulate the neurons, you see all the different mini columns here, right? 16 mini columns because 16 hypercolumns, and every one of those has one selected mini-column. Then over this time window where we are stimulating, the Hebbian learning rule will learn that the firing of these units is actually correlated. It's going to update the exponential weighted moving averages, the priors and the posteriors and the co-activation probabilities. And as a result, the network now has an imprint of this activation. It's a memory of sorts. And that leads to autogenic reactivations. So these brief bursts of reactivations that you see here, they tend to actually be gamma bursting, very similar to what you see in biology, because the basket cells, these strong inhibitory pools that you saw on the units, they will locally shut off the activity. Right? As soon as one mini-column becomes strongly active, it's going to silence the activity in its neighborhood. That is not going to stop the attractor after the first time, because there's going to be out-of-phase excitation from more distant mini-columns, which are going to deliver incoming spikes. So that's why the attractor will keep going for a while until the transmitter is depleted. So it's mostly synaptic depression that switches these off. And so then after some time of recovery, you can get random reactivation events again. Now this is just storing one pattern here, so that is relatively boring. You can do more with that. So we built a wordless learning model. So there's a common wordless learning task where you give people 12 words to remember and you interspace them with 2 seconds, and then you simply ask them how many, write down the words you still remember, and you get 45 seconds to write them down, or to say them out loud. It's a common wordless learning test, and you can do this with people. Well, you can do this in a model now too, right? So you're now teaching this little cortical sheet, not one pattern, right, but many patterns, and in the silence in between, the second of space in between the words, the network can do whatever it wants. And what you indeed then see is that patterns that you trained now start reactivating in between. That is important because the network learns from its own activity, right? The network produces firing with statistics that match the input it has seen, and it relearns its own learnings. So it's sort of an auto-refresh mechanism, whereby memories can now last a lot longer than the time constants of the learning would suggest, because they can self-refresh. If you do that with 12 items, you can then analyze, well, what do the distributions here, which patterns do I actually recall? And it turns out that you very nicely match the free recall curves that you see in people. So typically there's a strong primacy and recency effect of those 12 words. You're going to be very good at remembering the first 3 words and the last 3 words, and typically the words in the middle of the list fall out. This network reproduces that effect because the first items now get an advantage in that they can self-activate and self-stabilize in the network, growing strong correlatory weights. And the last couple of items have an advantage because they were just trained, so their synaptic traces, right, were strong. So their estimates for the priors, posteriors, and co-activations are strong. And the middle ones drop out. Same with conditional probabilities. So typically when you remember item, you are very likely to also remember the item just after and just before. And so these networks have a similar effect. And so you can match them up with cognitive studies. That is obviously a bit of a toy application, but the reason why this is interesting is because you can still match the electrophysiology of real recordings here. So you need to answer, are the weights that you are growing here, right, with this Bayesian learning rule, are they actually realistic? Right? Say your learning rule now learns, 5 millivolts, postsynaptic potentials. That's, kind of unheard of, and so you can't really have that. And we find that in the regime that these networks operate in, when they fire like 4 or 5 spikes, you get very nice, 1.5 millivolt excitatory postsynaptic potentials. So you can go back and forth between ideas of cognitive science, electrophysiology, and machine learning. And then you can get that published in a very nice, Journal of Neuroscience and get a PhD for these kinds of things. You can also go the other way around. I'm sorry, there's a question?
What determines the replay interval? Is that the biological parameters that?
Yeah, mostly the depression time constant, which for cortical neurons is like on the order of 500 milliseconds.
So it's an intrinsic property of the circuit.
Yes.
And you need to pair the interval of the stimulation with that interval.
No, you don't. No, I mean you can stimulate at any interval that you want, but the items, like an item that is just activated, will not reactivate for at least 500 milliseconds. because the synaptic resources that are necessary for the activation of that item will be depleted.
Right, so if the entire sequence was played in a very short interval before the first replay of the first item even happened, then it failed to learn.
No, you would learn the sequence instead. That's actually what Phil Tully did for his dissertation. He showed that these networks cannot just learn, lists and show primacy, recency, conditional recall, but they can also learn full sequences. Because you would associate all these items with one another because you play them so close to each other. And it is different in my case because I actually intersperse them with silence, right? Like in the wordless learning task. In the interest of time, let's move on. So you can take this one step further to start, instead of starting with a sort of machine learning thing and then showing that you can do cognitive things with it. You start with a cognitive idea. Something like this, like role binding. So if I tell you that the name of my parrot is Charlie, then you won't be surprised, by, I don't know if I say that Charlie can fly, or maybe you can even tell me that Charlie probably can speak. Because you know these concepts and you were able to form an associative memory very quickly, linking two concepts that you already have. Probably heard the name Charlie before, probably know what a parrot is. You're capable of putting these things together very quickly. It is rather unreasonable to assume that the neocortex already has, that the structures that are implicated in short-term memory already has structures set out for everything you might theoretically learn. It is much more reasonable to assume that these structures are built online when you need to learn them. And so on that principle, you can now use a fast Hebbian approach to build such a model like that. So now you set out and you start, okay, where do I see stable long-term memory of sorts? Let's say for visual items, right? We have areas in the inferior temporal cortex, which are sometimes referred to as the long-term memory storehouse for visual memory. And maybe you want to link that with some other long-term memory structures, but you want to do that with an area that is known to not be so specific and to be fast changing in what it is selected for, like dorsolateral prefrontal cortex is highly involved in working memory. Working memory tends to be impaired when you lesion it, when you damage it. So some speculative model you could say is, well, you have some fast learning units, right, with Hebbian learning capabilities now in prefrontal cortex, and you interlink them with two networks that have already many stored items, long-term memories that are stable structures, that you can now flexibly co-activate and build into pairs or whatever conjunctions of item activations you want. Then you take some data on cortex. Well, how many connections are there actually between those areas, right? So if you take macaque data, right, these areas are some 400 millimeters or so, like from one another. So what's the length of the wiring? What are the connection delays? How many synapses are there? There's good experimentalists who are doing great work on that, and you try to put that together with the neural models, the synapse models, a lot of constraining electrophysiology, which I mentioned, and all importantly a Hebbian SDP rule, and then you generate a big synthetic model where you're going to need some big supercomputer for that, obviously, because that's going to be expensive to synthesize that much, and then you build a model of that. Some of you who know a little bit about cortical architecture will already see that there's now different cell layers here, so this is a super granular model that actually differentiates different pathways. And so you are simulating these different mini columns, right, with an extent of like some 30 neurons in layer 2, 3, and some 30 neurons in layer 4 maybe for the input layer. And you have already embedded long-term memories, recurrent structures, right, embedded in these two long-term memories, and you now have a flexible short-term memory system that is connected with plastic back projections and plastic recurrent connections to learn and bind associations. And so then you can actually use that. So I don't have time really to show all that data, so I'm just going to wrap this up. When you do working memory encoding, you co-activate two items in the long-term memory. As a result of that, with some small feedback delay, you're going to start seeing these gamma bursts happening in prefrontal cortex, which we can obviously then compare to macaque recordings. So Miller Lab at MIT has some great recordings on that. One of our PhD students went there. And then you can ask, well, what happens during maintenance, right? So when you're now maintaining these items, does the prefrontal cortex actually lead now the posterior areas sort of to keep those long-term memories alive? So you're holding on to these structures that you have now bound. And then during recall, where you can see the associative effect of these, I can just give you a trigger. I can just stimulate one item in one of the networks, say I say Charlie, right? And then with some feed-forward delay, the prefrontal cortex is going to retrieve that Hebbian learned index to the memory, right? So that it's not really the full memory content, it's just enough neurons to bind the full conjunctive representation. And then with some feedback delay, the prefrontal cortex is going to retrieve the associated item from the other cortical area, such that I don't need to be able to learn these connections here, as long as I have a dynamical hub in prefrontal cortex that can bind these items. And that, because the spiking networks provide a lot of opportunities to match with electrophysiological data. These models are still evolving, right? They started out as one-layer network for classification. They acquired, a lot of cortical detail. We used them for reinforcement learning to simulate basal ganglia and action selection. I started Phil Tolley that I told you about, right? Built this spike-based version of the BCPNN learning rule. And I've built a lot of systems on top of that. That work is not finished yet. There's people working with it. And so let me quickly acknowledge some of those. My two doctoral supervisors, obviously my two main institutions where I did my PhD, the Royal Institute of Technology in Stockholm and the University of Edinburgh. So that's Phil Tolley, who developed this spiking implementation of the learning rule, two of my academic mentors, Nikolaos Chrysantidis, who's now starting in Stockholm and taking over much of my work, and author-collaborator Pavel Herrmann. And with that, I'm done. Thank you.
We still have about 9 minutes.
So we have 9 more minutes for questions.
So you talked about the memory model, right? And so let's suppose we have those memory athletes that can learn like hundreds of words with perfect recall within like minutes, right?
Right.
And so according to this theory, it would mean that they're associating those words in the neocortex instantly with a visual stimulation or visual memory map, right? It's based on like they have like a memory map in their mind and they can associate those two, and those two are getting accurate. How are they able to switch so fast to different words in the neocortex instantly and map those to their visual, like the data in their visual cortex or visual memory?
It's a good point. First of all, one should point out that these kinds of tasks that you are describing eclipse what working memory does. Working memory is like 3 to 4 items, right? Yeah. And then maybe if you're bunching them, you can get to more with that, right? If you're leveraging, tools that you have, like the phonetic loop, like buttermilk, egg toast, cheese, right? You can just keep going like buttermilk, egg toast, cheese, buttermilk, egg, without knowing all the items, just because you have a dedicated circuit for phonetic repetition. Yeah. So everything beyond that is clearly not working memory anymore, yeah. And you're going to need to explain how that works. I think it's still useful to think about it in these associative terms, because when you ask these people how they do these tasks, right? The most common method, the method of Loki, I think in America mostly known as the palace of the mind, is this idea of mapping objects that you want to remember or sequences. You're learning the number of pi. I had a history teacher who was like making a Guinness record attempt at that. And you're mapping them to different places inside a house, or like in his case, a whole street, because too many numbers in pi, you need to all put them somewhere. And so they are mapping things onto already existing structures, which to me is a strong indication that working memory really is about this interaction between long-term memory structures you've already built, and you're leveraging them to put in new things. And so, in some sense, we abandoned the original discussion of short-term and long-term memory in favor of working memory, in part because of this. Because it's not really just about the time, right? It's about the operability of the memory, what you are doing with it. And in that sense, it's helpful to understand working memory as leveraging the existing structures you already have, right? You are not creating working memory from whole cloth. If I had given my speech in Chinese, it would be very hard for most of you to recite or mention, maybe the 5 most salient points of this talk. The point is memory encoding, working memory encoding in particular, is really bad when you don't have existing concepts to bind them to. So it's I understand it doesn't really answer your question, but I think it shows that we need to think about working memory a bit more holistically.
If I look at this from eyes prejudiced from CNN learning, I say, gee, in that case, the learning rates are tiny. It doesn't take 1,000 examples or 10,000 examples to learn something.
Right.
Here, my God, I'm learning it in a single exposure. There are many, many other differences, but this difference is so dramatic. Can you? And if I dial up the learning rate to approach even a tenth of that, the thing goes into wild nonsense. Why is this better? Why does this avoid that problem?
Yeah, I think it's one of the biggest topics sort of to talk about, right? This wild order of magnitude on which we have memory, right? Because we are encoding things like, I can flash you a card from a card deck, I don't know, an ace of spades, right? And put it down and you can tell me what it was, even though I just showed you for 200 milliseconds. But you will also might remember things from 2 decades ago. So you have memory on the order of 6 magnitudes, right? There's no artificial memory system that can do that. Yet somehow our brain makes it work, and it makes it work by a lot of filtering, right? The vast majority of the things that we remember are forgotten. And the synthetic systems that we are building are not really designed for that. There are networks that forget, then often catastrophically. But this idea that you should do what these networks do, where you have like an exponential weighted average which dies down. So unless you refresh or transfer into a more lasting form of memory, which has a slower updating, you're gonna forget. Much of biology suggests that that is indeed the case. So you have prefrontal cortex that shapes its activity and builds these highly selective assemblies very quickly, one-shot learning. But then you also have hippocampus, which can, like build change connections within minutes. And then you get sleep-dependent memory consolidation into a very slow learning distributed neocortical substrate. And so maybe we really do have plasticity on just vastly many different orders of timescales. And if we build synthetic systems like that, maybe we could get there, where we could have one system do one-shot learning, but still learn models of the world, right, to solve the stability-plasticity dilemma. That's how I would think about that.
Just a question about the Bayesian computation. So here, a cell assembly that represents a probability distribution, you basically map a category into one neuron, right? So it's discrete. How do assembly represent continuous probability distributions? That's the first question. And second, do you think the number of neurons is kind of limited, or how do you express like classes with many classes with fewer classes?
Right.
Another question is, Bayesian computation is well known to play a role in sensory fusion, like multi-streams of uncertainty integration. So have you done any work demonstrating that?
Right. So to answer the last question first, no, I've not worked on that specifically. I've obviously, I know colleagues who are working on this problem, and it's very interesting to see if we can interest them in these kinds of models. But I can speak a little bit to the first question. So obviously, yes, it's true, we are mapping somehow to discrete categories. And well, that is fine for maybe early cortex, like visual cortex. It gets problematic in higher area. What I didn't show you is how these sparse activations in prefrontal cortex actually look like in terms of spiking activity when they bind items. Because one, they're very sparse. There's 4% or so of the neurons that then get selected. And the other one is that they are very fast changing, right? So even though it is discrete, we don't need many more neurons, because in fact working memory is very low capacity. Its strength is not capacity, its strength is agility and speed. And so what we see when we overtrain these networks, when we train them more than 4 or 5 patterns, the structures in prefrontal cortex are going to be reused for other things. And that is exactly what we observe when we record from prefrontal cortex, that in one task these neurons are coding for, the size of the object and its color and orientation, and in another task it's going to code for the rule of the game currently and the some other aspect of the different tasks that they're now engaging with. So they very quickly remap. And we have shown exactly that in these networks. So you don't necessarily need a very big network if you have a lot of flexibility. And of course, it's a little bit synthetic to say there's long-term memory, which is eternally static, and there's the super flexible memory system. Obviously, in the real brain, there's going to be a gradient of sorts, and there's not really a dedicated long-term memory area and a dedicated short-term memory area. So all of these are, purposeful simplifications. The other thing with the interval code is a bit more tricky question, where how do you go to continuous variables if you now want to represent a continuous distribution rather than discrete ones. In some ways, we've made it very simple for us in that we've leveraged the powers of attractors here to do pattern completion. And so we have discrete object, and either the object does get recalled because the attractor kicks off, or does not get recalled because the attractor does not kick off. What do we do with the places in between? It's a fascinating question, and I don't have a clear answer for it, at least not on the basis of an attractor theory of neocortex. Obviously, one can argue there are bump attractor models that have nicely shifting representations. I find them somewhat artificial. The thing is also, the whole thing about neocortical architecture is very discrete, right? All of the neurons inside a mini column are not just selected for the same item. They have the same genetic progenitor cells. So they are built as one unit. And so I think we cannot cop out by these bump attractor models. We have to say what these units are actually doing. And Numenta has a much bigger vision for that, in part because they attribute a lot more power to the individual neuron. But there's many ways to talk about that. I think that's an important question we need to answer as cortical theorists.
You touched on the role of hippocampus in consolidating long-term memory.
Mm-hmm.
That seems like sort of burning in memory, but the working memory model you're talking about relies on retrieving.
Mm-hmm.
Or reactivating
Right,
long-term memory.
depends on activity.
Does that have to be mediated through hippocampus in some way, or is it just
Well, I could imagine that hippocampus is listening to that, right? And many, hierarchical models, the hippocampus kind of sits on top of it. Prefrontal cortex is certainly high up the hierarchy as well. So these are areas that can bind a lot of activations from different areas.
Hippocampal activity isn't absolutely necessary.
No, it's not particularly necessary. You can do lots and lots of working memory tasks. There's wonderful work by, Larry Squire in San Diego, who's analyzed all these patients who have tremendous mediotemporal lobe damage. So the area where the hippocampus might get impaired too. And he's shown again and again that when the task does not exceed a rather strict definition of working memory capacity, namely 3-4 items, then you don't get any impairment from losing hippocampal function. As soon as the working memory task exceeds those demands, as soon as you really need to put things away for a while and retrieve them from a longer lasting form of memory in order to handle the task, you immediately see the deficits when these people have any amount of mediotemporal lobe damage. So to me, that is a strong indication that indeed you can divorce a strict definition of working memory from the mediotemporal lobe, but of course we are always working on that edge, right? Part of what you've seen here today will be encoded in hippocampus. Some of it is going to linger around a little bit in terms of reverberating activity, some of it lasting synaptic changes, and maybe some small fraction of this hopefully going to consolidate tonight when you go to sleep, right? Because it is
hippocampus is watching the experiment go by.
Yeah, in some sense.
Right.
It is astounding that during deep sleep, when you look at pattern reactivations, it's very nicely tractable in case of place cell experiments, you get hundreds of repetitions of prior day learned episodes, right? And the more important some particular episode, the more often it gets replayed. It's like hundreds and thousands of repetitions. So these are 3 Hz events, so there's 3-4 of these sharp wave ripples every second. And the whole time while you're in deep sleep. So that is a lot of replay, an amount that you could never practice that much, right? In part because it compresses whole behavioral episodes into these 100 millisecond long nested oscillations. So we have very strong evidence that hippocampus does indeed do that consolidation. It is also clear that you don't necessarily need it for working memory, but we somehow need to explain that bridge where we violate what working memory can take. How do we export things there? Right? So how do you play a game of memory and still know more than the last three cards that were folded up? How do you do it? Right? That is a fascinating question. I don't have clear answers on that, in part because all of my recent work has been cortical, and so I've not looked all that much into hippocampus.
Can I thank Florian again?
I'm happy to take any questions later.
We'll have also some time.
I'll be around.
All right, let's switch you over.
Thanks, Florian.
Thank you.
Oh, that was fast. Okay. I was saying, while you set up, I was just gonna say. So I think a lot of people, I forgot to thank Lumenta actually, who's sponsoring the event with drinks and food. So thanks to Ty. There was a whole bunch of Lumenta team here, and this whole meetup grew from our desire at Lumenta to accelerate the adoption of neuroscience findings and principles in artificial intelligence. We believe that's what it takes to get to artificial intelligence, and what we want is to promote neuroscience in artificial intelligence in all kinds. Right? So we don't talk only about the work at Lumenta, but we talk about neuroscience in more general terms. So the meetup, so Lumenta is sponsoring the meetup, but the meetup is more a general term. So we usually start with a more neuroscience talk about the brain, and then we move on to machine learning. So if you're here just as a machine learning researcher, and Florian talk was a bit hard, I feel you. It was a bit hard for me as well, but it's really fascinating. Like I hear this, we have students that are here every day, and I'm learning bit by bit. And I find that very fascinating how much we don't know about the brain and we think we know in machine learning. So Thomas is going to give a talk more aligned with machine learning. So if I can briefly introduce you. So Thomas Miconi, sorry if I is a research scientist at Uber AI Labs, and he's also affiliated with the Neuroscience Institute. And in the past, he was a research fellow at Harvard Medical School and at the French National Center for Scientific Research. He earned his PhD from the University of Birmingham, research on evolutionary algorithms, evolutionary robotics, and artificial life. Thomas is a prolific researcher with dozens of papers published and many citations. And we are pleased to have you here talking about your work. So thanks, Thomas.
Thanks, Lucas. Is this thing working? Yes. Hi, well, thank you, Lucas, for the kind introduction. So today I'm going to talk very briefly about something that I've done both at the Neuroscience Institute and at Uber, around the question of using Hebbian plasticity in neural networks trained by gradient descent in order to generate networks that can learn quickly and automatically after their initial training. So this all starts from a simple observation, which somebody here has also made, which is that traditional deep learning networks, which have recently produced amazing results, are usually trained very slowly over many, many thousands or millions of examples. And here I'm talking about AlphaGo 0, the machine that basically cracked Go. Also ImageNet, the famous image recognition competition, which has millions of images. Those things here are hopelessly outdated text processing databases. The more recent results use much larger things and train networks with billions of parameters. So those beautiful results of deep learning come around by using a lot of data and a very long training. This is in stark contrast with animals and living creatures, which can learn very high dimensional data very fast and very quickly. I'm going to show an example that I like. This is a rat in a maze that he has never seen before. That's the first time it sees the maze. And eventually, exploring the maze, it finds a food cache. And then, immediately, it goes back to that cache. And then, after a few visits, it goes there directly. Bam, bam, bam. Very fast. And it has memorized not just the configuration of the maze, but also the path to the food cache, like maybe in 2 or 3 trials, basically. again on a maze that he has never seen before. No thousands of examples, no millions of trials, like we do all too often, including lab. So how does that work? Now, as we have seen in part through Floran's talk, in the brain, the main support for durable lifelong memories is synaptic plasticity, which consists in making the connections in the brain change automatically as a result of neural firing, which is essentially as a result of experience indirectly. And the main form of plasticity in the brain, not the only one, but the main one, seems to be Hebbian plasticity, generally summarized as cells that fire together or wire together, or known as term. Hebbian, Donald Hebb himself put it in a slightly different way, the way he said it, if I remember correctly. If a cell repeatedly takes part in making another cell fire, then their connection will grow. There is a causal language which is absent in this simplification. But nevertheless, the general principle is pretty sound. If you have two cells which tend to be correlated, and one comes before the other, and they already have some connection, the connection will grow. Whereas they tend to be anti-correlated, the connection will tend to decrease. Now, something that's pretty striking about this type of rule is that they are totally unsupervised. It's just local firing, nothing else. And yet, this very basic unsupervised learning at the local state results at the scale of the whole brain into very efficient, goal-directed, behaviorally effective learning. So how is that possible? Well, the reason is that even though this learning is unsupervised at the scale of the local connection, it doesn't happen in a vacuum. It happens in a carefully designed structure, the brain, which has been designed across very, very, very long periods by evolution in order to produce an overall structure in which this unsupervised learning results in things that are useful and efficient. What evolution has done in general is pretty much everything, of course, but in particular, it has designed the overall connectivity pattern between the areas of the brain. It has set the initial weights for the connections, at least in a statistical sense. It has also set different amounts of plasticity in different areas of the brain. Prefrontal cortex learns very fast, hippocampus learns a bit slower. Inferior temporal cortex learns very slowly, but it does learn if you put the time into it. So lots of different time scales, a lot of different amounts and time scales of plasticity in different regions of the brain. And because all of those things have been carefully designed and tuned by evolution across a very long period of time, this allows this simple, basic learning rule at the local level to result in very, very powerful and efficient learning, goal-directed learning at the scale of the animal. So what we want to do here is take inspiration from this, but instead of using evolution to design our networks, we want to use exactly the same methods which have produced so beautiful results in those recent reports on machine learning and artificial intelligence. We want to use just plain gradient descent. Like, we're going to train a network, but instead of just training the network, we're going to train both the weights and the plasticity of each connection in order to get an overall network which will be able to just leverage automatic hidden plasticity to learn automatically during its lifetime, like the little rats. So how do we do that? To do that, we just need one thing. We need to specify Hebbian plasticity in each connection in a way that's differentiable. If we can differentiate through it, then we can train it with gradient descent, and we can use all those beautiful techniques that are still being published so very frequently right now. So this is there are many ways to do it. That's the way we came up with. This is the normal equation for the activation of a neuron. It's just the standard normal equation that you will find in any neural network. The output of a neuron is equal to the weighted sum of its inputs passed through some kind of nonlinearity, hyperbolic tangents for these purposes. Exactly like in a normal neural network, the only thing that's different is what we put in the weights of each connection. So normally, in a standard neural network, you only have this W here. For each connection, there is a W parameter, which is trained by gradient descent, and which tells you how strong this connection is. And once the network is trained, that's it. It remains fixed and it never changes. Here, we still have that. We still have a baseline, so-called birth weight for each connection. But on top of that, we have a lifetime varying quantity here, which is the plastic component of the trace. So in each connection, we have a fixed component, something that's just trained by SGD, and then afterwards, during the lifetime, it doesn't change. And on top of that, there is a plastic component based on a Hebbian trace here, which is automatically updated during the lifetime in a Hebbian manner as a result of the product of the firing of the input neuron and the output neuron. This is the precise equation for updating the Hebbian trace at any given point in time. It's just a running average of the product of the input neuron by the output neuron's activation. Presynaptic, postsynaptic.
What is clip?
Sorry?
What is the clip function?
No, clip is just something that prevents it from diverging to infinity. In particular, basically, if it's larger than 1, clip it to 1. If it's lower than -1, clip it to -1. It's just that. And because otherwise it's unstable, famously. So, again, to emphasize the difference between all those parameters. The structural parameters, the one that you train by gradient descent and backpropagation, are W and alpha. Again, W is the baseline weight, the initial weight of the connection, and alpha is how plastic this connection is, plasticity coefficient, we call it. Notice that if alpha is 0, then the connection is just a simple W, and you just have a normal neural network connection, which is not plastic at all. Once it's trained, that's it, it never changes. But if gradient descent decides that it will be useful for this connection to have a non-zero alpha, then this connection will start at birth, so to speak, for each episode with a certain W, and then it will change over time as head is going to change. And this will affect the total weight for this connection. Okay. This may be a bit fuzzy. I just want to show that the overall thing is very simple. First, I'm going to show the algorithm for training those networks. Again, you see, very simple. Here I'm using episodes and lifetime interchangeably. It's the same thing, basically. I'm going to show examples of what I call an episode or a lifetime. But basically, for across lifetimes, at the beginning of each lifetime or episode, you set all the Hebbian traces to 0, and then during the episode, you simply run your network at each time step. If you get a reward, you store it, or if you have a certain loss, you store it as well. You update the Hebbian trace, which means that the plastic connections are going to change automatically as a result of the input and output, etc. You keep doing that for your whole episode. At the end of the episode, you have a certain reward or loss that you have accumulated during this episode, and you take the gradient of that across alpha and W. Again, the initial weight and the amount of plasticity in each connection. And you take a gradient step, and you start again. Again, in the metaphor of evolution and lifelong learning, this here, the whole loop, is evolution across many lifetimes, and this is a lifetime. Yes, and again, to show that it's really, really, really simple, I'm showing the actual implementation on a standard recurrent neural network in PyTorch, 4 lines of PyTorch. That's all you need to make plasticity in a recurrent network. All the rest is a standard implementation for recurrent network. The only thing that you need to add is the alpha components on top of the W weights. You need to specify them. You also need to initialize the Hebbian trace for each connection. Then you take into account the Hebbian components for the activation of the neurons, and you update the Hebbian trace. That's it. 4 lines of PyTorch. You know, it's very easy. All the code is online if you want to check by yourself. Yes, that's it. So, I wanted to show a couple of experiments that we did to prove that this thing actually works. The first task that we set to it is a very traditional task in Hebbian learning. It's image memorization. The task is to memorize a whole images that you've seen just a few times, and then being able to reconstruct them when you see just a partial version of the image. So for each episode, I show you 1 image, 2 images, 3 images. You need to memorize them, and then I show you a partial version of one of those images, and your goal is to reconstruct the missing thing from memory. Again, I insist on the fact that we're not just training a single neural network to memorize a fixed set of images. Those are images that were never seen during training. We want to train a neural network to memorize arbitrary novel images that was never seen before. And we show that this network is, just to be precise, the architecture is a recurrent network. Each neuron corresponds to a pixel. So the activation of the neuron tells us the value of that pixel, and that's how the neuron tells us what it wants to put here. Yeah. Those images are 1024 pixels, so because recurrent networks are connected all to all, there's 2 million parameters in there. So this is proof that this thing works even for reasonably large networks with millions of parameters. And we just showed change 3 times in random order, just a detail. Here, you show the process, you show 1 pattern, 2 patterns, 3 patterns, and the partial pattern, and it reconstructs the rest automatically. It's just to show that it actually works. In terms of quantitative results for this task, the interesting thing about this thing is that non-plastic recurrent networks cannot solve this task. They're completely unable to do it, I tried. If you use actual LSTMs, which are much more complex recurrent networks, they can kind of solve a much simplified version of this task with, instead of full images, 50 bits binary patterns. That they can do. And even then, they're not very good at it. Like this is the trace for an LSTM. This is a standard RNN, we just count. And this is the plastic network, vertical. Like it learns immediately. Also, we verified that being able to actually train the plasticity of each connection is actually useful. So those alpha components that I showed you really do something. Being able to train the individual alpha of each connection makes you better at this. And as we will show, as we'll see in a minute, it can also make you much better for other tasks. All right, yes, this is the other task. That's, yes?
So the choice of eta.
Eta. It's arbitrary for now, but in a minute I'll show you a better way to do it. So the previous task was basically some kind of supervised lifelong learning. I'll show you an image and I want you to reconstruct it. Does it work for reinforcement learning? Well, so we tried a very simple task, which is a maze exploration task, very similar to the little rat that I showed you first. So it's a maze exploration task. The maze is always the same. It's just this simple grid maze. From one episode to the next, you have a certain reward, which can be in any location in the maze. The agent, which is this yellow thing here, its goal is to find the reward, and once it has found it, it gets teleported at a random location in the maze, and it needs to go back to the reward. Then teleported again, it needs to go back, etc. So the maze is always the same. So during your life, you don't need to memorize the maze. You can store it, so to speak, in your innate memory of the W's, the fixed component. But the position of the reward is unpredictable, and the only thing that this agent can see is a small neighborhood 3 times 3 around itself. So at first, when it's dumped into the maze, it doesn't know where the reward is. It needs to explore, find the reward, and then, when it gets teleported, go back there as often as possible during an episode. Initially, of course, it's completely random, so it just moves randomly, I guess. Once it has been trained, it's very efficient at going back to the reward very often, once it has found it. And again, first we confirm that plastic networks can solve this task, that non-plastic networks are very, very bad at it. And we also show that if all the connections were equally plastic, you might think that maybe it might be able to learn it, but actually it really doesn't. You really need each connection to have a specific trained amount of plasticity to be able to solve this task. The simplest explanation is that not everything should be plastic. Some things should be there to store the memory, and other things should be reliable and fixed in order to ensure basically the logic of the thing. You need to have the logic component and then the memory component. The logic component should be fixed, and the memory component can have some plasticity. Presumably, that's one reason for why this thing works much better. It's just a hypothesis. We're going to try to test it thoroughly.
So is it just 2 different alphas that are? If your hypothesis
in most of the tests, there's a whole variety of alphas, so it's not binary.
It's not just 2 different.
No.
Things, yeah.
For the image memory task, you can interpret the patterns of the alpha connections, and it does some beautiful things. It's very simple. I refer you to the paper. I'm going to try to explain it, but when you can interpret it, you can see that it does some really clever things about the different values of alphas for different portions of networks. I encourage you to check out the paper. Okay, so those are 2 tasks. Okay, so now we have shown that plastic networks can be trained and can learn arbitrarily, they can learn unpredictable stimuli that they have not seen during their training very well. But in the brain, plasticity, even though Hebbian, it's unsupervised, but it's still controlled by the rest of the brain. There are various chemicals in the brain which determine at each point in time not just the sign, not just the magnitude, but also the sign of the plasticity. So we have this Hebbian plastic rule, which determines roughly how much change should be applied to a certain connection. But because of those various neuromodulators, dopamine, norepinephrine, acetylcholine, many of them, the brain can control at any point in time when to be plastic. That is, if you want, we all know it, sometimes our brain is very good at learning some things which are very important and at ignoring other things which are less important. Those are various pieces of data from actual neuroscience. The simplest version is this one, where this is a plasticity experiment where you basically stimulate some connections and you show that there is an increase in the connectivity weight between those two cells. Without dopamine, that is without the neuromodulator, the increase is very small. In the presence of dopamine, the increase is much larger. So basically the brain can control its own plasticity. How do we implement that in our model? We can do it in a very simple way. It's the eta component here, which determines basically the rate of change in the brain. Just make it the rate of change of the plasticity. Just make it an output of the network. So, yes, that is. In the network, you will have one or a few neurons which are assigned to be the computers of eta. Now, there are many ways you can do it. You can have a single eta for the whole network. Different parts of the network can have different etas. It depends on the task or whatever you want to do, but the important thing is just make eta, that is the rate of plasticity at any given time, an output of the network so that the network can control its own plasticity in real time. We call this framework bad propamine because we like cheesy pens. So does it work? Yes, it works very well. We have various experiments in it. You can check out in the paper. One result which is quite notable is work that we did with Aditya Arora, with also at UVer, on language modeling. This language modeling task where you need to predict the next word that's going to be seen in the corpus. It's a standard task. The architecture is LSTMs with plasticity. We managed to put some plasticity in LSTMs and with neuromodulation as well. Yes, so in all of those cases, the number of results is equal, and basically we show that putting plasticity in STMs is a drop-in addition to STMs, which seems to make them perform better. So we are pretty happy with that. But again, those results are hopelessly outdated with those enormous transformer-based architecture which were just published last year. So we're still working on that. So in conclusion, we've shown that with gradient descent, we can train networks that can keep learning after their initial training, can learn unpredictable stimuli that they have never seen during that training, and do it automatically and efficiently. And we show that they can equal or outperform non-plastic networks, including LSTMs, much more complex architecture on various tasks. So we show that this is an efficient, nature-inspired approach to the problem of meta-learning, learning to learn, which is a hot topic these days in machine learning. And importantly, it's very, very, very easy to implement, and all the code is on GitHub at those two addresses. But we also show the papers that were published at SCML and ICLR in the past year. So that's it. That concludes my talk. Thank you for trying
So in the previous case, eta is just one number for every case, right? Or is it different for different layers?
Experimenter's choice, really. You can put whatever you want. It's just initially in the initial version, it's just a number. You decide what it is for any part of the network.
So I'm done with experiment with like continuous data. So I wonder like if you present like sequence of data that's changing faster than slower, maybe the eta will be learned to go fast and
That's a good question. We didn't look at that. We didn't look at it specifically. Something perhaps related, which is in the bipropamine version, we show the actual amount of eta, which is again the control of the network at any point in time. And we show that it reflects various parameters of the experiment at any given time, when it needs to learn something, etc. But it's very messy. Like the way the network does it is not necessarily what you have predicted beforehand. And from one trial to the next, it changes a lot. It's quite interesting. Again, you can check out the paper. We have this figure, basically.
So how does the Hebbian trace compare with what Jeff Hinton calls fast weight? I mean, is it the same thing?
I always get this question, but this thing was initially published before fast weights, which is very basically, it does compare with fast weights in a very simple way. Fast weights is, I need to go back there, but fast weights is a green trace here. It's when everybody has the same alpha. When the fast weights approach, there's no alpha, the plasticity is not trainable. All the connections have the exact same amount of plasticity. So the overall design process cannot sculpt connectivity and the amount of processing of different connections in order to have both logic and memory components. So yeah, that's the main difference. This thing is trainable, the alphas.
Sorry, last question.
Sure.
Any application on non-recurrent architectures?
Yeah, we have some. We show that it also works for feed-forward networks when you want to memorize stimuli, basically. We try it on the omniglot task, where you have basically to memorize very quickly new letters from various alphabets that you have never seen before, and associate them with the letter. It works pretty well. And again, purely feed-forward network. No recurrence.
Where is the future research direction you're looking for this work?
Oh, for this thing, right now we're working on other things, but basically the main thing is to work more on Here I'll show you the simplest form of neuromodulation. There's a more complicated one where neuromodulation affects the past, basically, where it's retroactive. Yeah, this is when the dopamine was applied long before the event, nothing changes. When it was applied long after the event, there's no change. But when the dopamine is applied just 1 second after the event, then you see the change. We have actually implemented that, and it is in the original paper, but basically it shows that, again, it's very easy to implement. This thing is very flexible. So you just, as soon as you have the equation, you can literally write it in PyTorch, and it just works. So yeah, those are the things that really are interesting, trying to find more flexible and more complex forms of modulation, and see what those things can do in more complex reinforcement learning tasks.
I have a question. Are you emphasizing how easy this is to implement to get other people to do this on bigger and more recognized data sets? Because like when we looked at this paper, we were talking about it in the Mensa actually. I mean, one of the biggest criticisms also online was exactly that, right? That it's nice you showed it for this. It's an intriguing mechanism. Not even looking at this hilarious pun of dopamine. I totally love it, but indeed, like in order to impress people, you need to use it on something that people recognize, right?
That's one of the reasons why Aditya started to work on real benchmark tasks like the benchmark for language modeling. Like, there is
so that is going on. So
yes,
we can expect something like that.
Hopefully.
Okay. And then maybe one more question about you use the clip function to avoid the runaway of your Hebbian weights. Obviously, there's different ways to get around that. In my case, I get around with that with a logarithmic weight, so that can't shoot into the sky. And obviously, but there's many different approaches to this.
Yes.
It always seems to me that clipping a weight is somewhat brutal because I have the sort of the fear that you're losing some valuable information when you do that, because you're just cutting it off.
It's a
so have you explored alternatives?
Yes.
Particularly given that in neuroscience, like obviously there's a maximum size, you know, like a synapse will grow to. But there's a lot of homeostatic mechanisms, both at synapses as well as neurons that control that. Right? So there's feedback mechanisms that will, shuttle it back down when it gets too extreme.
We tried various forms of soft clipping, where the weights always increase, but increase by smaller and smaller amounts as you get to the left. We tried that in various ways. Hard clipping was very well. Hard clipping works just as well or better than complicated things that we have understood. We hypothesized that the reason why it works so well is because we're not just throwing a random we're not putting the system together ourselves. SGD, gradient descent, will force the network to remain in a regime where the clipping will not be a problem. Because, again, it's the whole meta-learning thing. Because we have this meta-learning outer loop outside, we can be a bit more tolerant with whatever we put in the inner side, because hopefully gradient descent will find the right regime for it not to be a problem. And empirically, it works better or as well as anything else with it.
Your language has been very modest as far as describing the value of plasticity. But would I be fair to interpret that in fact you're telling us that if you add plasticity, it really is a big improvement?
It's a big improvement for those tasks. It's not necessary. How could I say it? Those are standard neural networks. We are standard connections. As you know, recently there's been a lot of more complex architectures like attention-based mechanisms, transformers, etc. It's not quite clear how to put plasticity there. So will it also be a big improvement on those big new things? I don't know. For simple recurrent networks, if you put plasticity in it, it's going to work better. That's it. But again, research is very much going on. Yes?
It seems like when you're adding in the Hebbian, the plastic component, and then you have this sort of the fixed component. So there's the part of the weight that's learned from sort of the learning stage, and then there's the part of the weight that continues to adapt, and that's what the plasticity is. Is there a theoretical justification why you wouldn't sort of continue to dial it more toward continual learning and less toward that initial learning? Like at a certain point, you could just have it, all of the weight be plastic, and have it be just that way from the beginning? Because it seems like you have the first part of the weight that's learned during the training session, and then there's this other part of the weight, that's the green one, right? The green one, and then the Heb keeps on changing. So why not just have it be all Heb and always changing? Theoretically, you know what I mean? Like there's always going to be some amount that's fixed learning.
Then if the alpha is 0 for human connection, then you have no right pattern, right? You want to have some baseline weights which don't change again to basically do the logic.
Right.
Basically printed circuits that tells you how information should flow for the thing to actually, damn thing to actually work. Yeah, the W again is the birth weight, it's whatever you're born with.
The birth weight, so those weights haven't been trained to be
that? They've been innate weights, they've been meta-trained. It takes a bit of getting used to the whole meta-learning thing, where you have those two the outer loop, which is slow a million times, and you have the actual lifetime, which is inner loop. So the W is the green thing, they have been meta-trained.
Meaning there's many different versions of this network, and then we figured out that sort of the birth weight, we sort of found an optimal birth weight by looking at different types of birth weights.
By SGD, by gradient descent, we somehow found an optimal, from some definition of optimal, value of the birth weight, which will allow you to do good at this particular task. Of course, if you put the same network on a completely different task, nothing's going to happen. That's a fact.
It seems like it's a big change, like against overfitting. This is really doing a lot. I mean, that blue line hits the ground when the other ones, take forever. So just based on your adding, you're doing this. You're with your 4 lines of code. So that seems like a big implication.
Have a look. If you think it's applicable to your task, whatever, sure.
Just a short comment. I think you would help yourself in communication by not using the term birth weight. Because if I think, so A, because it has a different meaning, but B, also because if you talk about neurodevelopment, right, and how these brain circuits that we are working with and that makes us these great, awesome adaptive learners, is really a thing that is also sculpted out of a much larger network, right? Like the connectivity of a 3-year-old child is roughly 100 times of what an adult has. And that is the result of a massive explosion of connectivity post-birth. So in that sense, sort of the substrate that we have to work with to learn on a daily basis now that we are adults, right, is actually a network that has been sculpted out of a much more complete network. And so in that sense, maybe it would be worthwhile, if I was in your situation, to spend a week reading like neurodevelopmental papers to try to adopt their language.
Yeah, that's
if you really want to make analogies like that.
That's a fact. The proper interplay between what we get innate and experience and how we get it is of course much more complicated just birth rate plus plasticity.
I mean, there is of course also connections we are born with. Don't get me wrong.
Yes, yes.
I think there's a big case to be made that much of that important structure that stays is also built just very early on, like in neonatal stages.
Yeah, so you mentioned that you applied this to the OmniGlot challenge. So I was wondering, how did that compare to a more traditional meta-learning method?
We tried it, we compared, basically it's roughly the same performance. We have the results and compare it with MAML and with a couple of metric learning methods, roughly the same performance. It's basically just a confirmation that it works, because OmniGlot is not a very difficult task. But yeah, it gets roughly the same performance as MAML or methods.
So what conclusion do you draw from that as far as the utility of this for image classification and like one or few shot image classification?
For image classification in general, it's probably not a meta-learning problem. If you're thinking of ImageNet or things like that, where you can have as much data as you like, that's a problem. For one-shot learning, the main thing is that this thing is very generic, and you don't need gradients at inference time. At inference time, everything is automatic. It's not even about inference time, because again, that's after initial training, you don't need gradients anymore, basically, and you can do everything automatically. In some cases, that's an advantage. In other cases, that's not an advantage. Basically, this thing is going to be very good when you need to learn a lot of very high-dimensional information very fast, because Hebbian learning is very good at that. We know it because of the trophy networks, because of all these things. So if that's your use case, learning very high-dimensional information very fast, this thing will probably be useful. For other tasks, maybe MAML is going to be much better, especially if you have to do some complex behavior. I don't know. So it's very task dependent. It's just an additional method for learning to learn quickly and efficiently.
Hey Thomas, thanks for your talk. It was great. So I wanted just to ask if you tried to compare this technique with other continual learning techniques, since it seems to be very related to them.
Yeah. For all the tasks I've shown here, the tasks are relatively short. The episodes are relatively short. There is one of our interns, Vitor-san, who works with this specifically for continual learning on much longer time horizons, and he has some results about it. He's trying to publish them right now. So yeah, whenever that comes out, first you can ask him, I'm sure he'll be very glad to answer, but yeah, some people are working on that.
But also to compare this kind of technique with them, or it's a separate work?
With who?
With this technique that you are suggesting to use, and the work that Vitor-san is.
Well, he's using this plasticity for learning. So yeah.
Thanks.
All right. Thanks, Thomas.
Thank you.
We have the room until 9, so there's a lot of pizzas, salad, drinks.
Plenty of beer too.
Floran will be here for questions. Some will be here for
Yes.
questions. Floran, can you publish your slides?
Yeah, sure. Yes.
And Thomas, can you publish your slides?
Can I what?
You publish those slides?
Just put the slides up. I was thinking of just putting the link in the event description in the meetup.
Yes, that would be great.
Sure.
Okay, awesome. Thank you. All right, thanks guys for coming. See you next time.
Just get the link first.
We have 20 people watching. Thanks for watching. Yeah, everything was great. I think so. Thanks for watching. I'll just leave it on until people go away.
Sorry you can't get
Yeah, sorry you can't have any pizza. That's good.
Memorizing sheets of letters.
Because I'm trying to do didactic learning. What's your last name? What? Portuguese name. Brazilian, not Chinese. I appreciate you so much for organizing. We're very excited. Your contact
I can give you a card.
Oh, you can do that.
Depending on thanks for organizing. Thank you.
There's one guy at
And what's your name?
Initially, there's a lot of future shape itself, and if I do zero, you're very good at snowing. After you learn the level of go, when you're snowing, you're learning when you're facing an opponent, you just need to know how to react. And then you can memorize it. So there is, that corresponds to the friction. For this particular test, learning to learn methods will not be very useful. For other tests, where you need to memorize something while you're playing, then maybe they will be useful. For group coordinate, for fully observable games, for more complicated games, for learning skills, when you don't have full observability of the whole space of the internet, our goal of the board games is to see everything when it's for example, for some video games, we need to move the camera around.
Things that got did also were not scaled.
Yes, it is a common
So then had two ends, a transmitting neuron and a receiver. In fact, then I could envision a network that sculpted itself.
This is Floran.
Because of things that are doing at scale. Not now imagine if the first changing vectors and each one has a one point each suppose that vector ask fun.
What's happening?
might be able to
that looks a bit like momentum in terms of the Hebbian action. The momentum is a bit of Hebbian action. It's a kind of momentum for the Hebbian action. It's a learning rate. The alpha thing, it's not a rate. It's a scale parameter. It is how large the Hebbian component can go. As I said, the Hebbian phase, so it's split between -1 and 1. So the alpha is already large. It's not a small or a small scale. That's the alpha that it's a scale parameter. It's not a rate parameter. So you cannot think of the beta you can. The beta it's a little bit far.
All of us are.
We haven't tried to look at it for different when you see a control parameter, you look at it over time, how it changes over time, various events. We have the figure which shows that.
The geniuses are the octopus. And I look at those and say, hey, when I think about what I think I know about the economy, which may be totally wrong, they are very different. Yeah, so do you know anything about that?
I'm as ignorant as you writing content, correct?
I'm not complaining.
No, I understand.
I would be interested to look at them and compare and contrast.
Yes, it's just I know since we want the thing to grab up all. That's why that's rodent data of like
let me make this personal.
we just pick those.
I come from New York, from the beach area, and I work with plants. Some head scratching, but I will not morally upsetting. Now let me switch to something else. First though, let me ask you for my question. I want to hear you say ownership with passion. Oh, good. Now he's ready for my question. I have a hypothesis.
Okay, guys, there's really nothing else going on here.
Based
So
on almost perfect.
thanks everybody for watching. Don't forget to like and subscribe the video.
My body, and I say, gee, I've got
I'm out of here.